Morning. Welcome to PRG Webinar 044, External Loads on Nozzles and Pipe Intersections. This is part 2. The content that you'll see this morning was written by myself, Tony Paulin, and Chris Hinnant. This is presented by the Paulin Research Group. Please send any questions or comments regarding this presentation to web044@paulin.com, and I'll be glad to try to answer your questions as soon as possible. We've got a little bit of a backlog now and a little bit of a change up in the system, so we're trying to get to all of the email questions. Please bear with us and let us know if we did happen to let one slide. If somebody doesn't get back to you within about a 24-hour period, that's when we try to answer all the questions. Some of the questions, discussions, or disagreements of general interest will be posted on www.paulin.com/webinar. To get electronic copies of these slides and a 1-hour PDH certificate, please send an email to web044@paulin.com requesting a copy of the presentation and a PDH certificate. The PDH certificate is intended to be used or is intended to be validated by your review of the document that you're sent for about 30 minutes, so that it collectively adds up to about an hour of review. These webinars only exist if people watch them, of course. Please email a colleague and ask them to join us if you would. It's through attendance that we make these things, or can make these things happen, and continue interest in them. Also, please support the folks that support us. That's Dynaflow in Holland, Fern in the UK, and Fuchs, W. Fuchs in Germany. Thank you very much. So to start, we want to say that pipes and vessels have a lot in common. This, of course, is a large diameter fiberglass piping system, but the basic rules of mechanics apply equally to pipes and to pressure vessels, especially for pressure and things like external loads. So today we're going to look at applying external loads and seeing large plastic deformation, or applying external loads and cycling too much and developing a fatigue crack and then a leak. So for piping, to evaluate external loads, it's a relatively simple matter because we calculate the stress, or at least our pipe stress program usually calculates the stress, and then compares it to an allowable. All of this done behind the scenes. For vessels, it's oftentimes a little bit more difficult because we have to determine the stress, we have to make sure we have our right allowable, then we have to make sure that the determined stress is less than the allowable. For vessels, this oftentimes means going out and running a WRC107 or 297 program, or a finite element program, making sure that we're computing membrane and bending stresses correctly, or membrane stresses correctly, or peak stresses correctly, and then comparing those to the proper allowables. In this diagram, I showed a nozzle intersection with a bending moment. We show how the bending moment applied at the center of the, in this case, the run pipe, provides a membrane stress through the wall and a bending stress component through the wall. At the concentration, i.e. at the toe of the fillet well, there'll be a peak increase on this stress magnitude. Notice also that I drew limits of reinforcement. There are things called limits of reinforcement along the header away from the nozzle, and then into the nozzle away from the header. Typically, these limits of reinforcement are some function of the square root of RT. Now, if I want to look at a simplified analysis for piping and compare it to a simplified analysis for vessels, in general for pipes, we say that the longitudinal pressure stress plus the stress intensification factor times the moment divided by the section modulus has got to be less than the hot allowable for weight and pressure moments and for pressure. SH, of course, is the hot allowable. Then also for piping, stress intensification factor times M divided by the section modulus, where M in this case is thermal moments, has got to be less than some allowable that is a function of the number of cycles, and the hot and cold allowable. If we look at fairly comparable analyses for vessels, see PD over 4T plus IM over Z, where M is just due to weight and pressure, has been sort of comparable to PL, which is the local membrane stress, less than 1.5 times SM, where SM is the hot allowable. This is the primary local membrane stress, less than its allowable, and it's allowable. Next, when we look at the fatigue or the cyclic stress for piping, we tend to compare that to PL plus PB plus Q, less than 3 SM average for the vessel analysis, and PL plus PB plus Q plus F, where this plus F is the peak stress component, less than the fatigue allowable, again from the vessel component. But now, can the stresses due to thermal expansion of a piping system somehow end up in the PL less than 1.5 SM category? In general, this is compared to the piping PD over 4T plus IM over Z less than SH, which is weight plus pressure. Can this include thermal expansion? If I go to the Section 8 Division 2 2007 code to try to answer that question, within the limits of reinforcement given by paragraph 4.5, which is essentially some function of the root of RT, we have 3 requirements. We have a PM classification that is essentially M over Z, no stress concentration, no discontinuity, and no I factor, that includes the restrained free end displacements. We have a PL classification that is the local membrane stresses, as we saw previously, that include the effects due to restrained free end displacements, i.e. thermal expansion of the piping system. Then we also have a PL plus PB plus Q classification, which we saw, that includes the effect of the restrained free end displacements of the piping system, i.e. thermal expansion. So according to 5.6 of the 2007 Division 2 code, the PL classification must include the restrained free end displacements of the attached pipe, which is typically considered the thermal expansion of the piping system, or the thermal stresses in the piping system. So if we go back to our evaluation, PL less than 1.5 SM, PL, according to 5.6 of 2007 Division 2, the primary local membrane stress must include the effect of the thermal expansion of the attached pipe. That again is a little bit surprising to us. If we look at these allowables again slightly recast, PL less than 1.5 SM, if 1.5 SM is 2/3 the yield, then 1.5 SM is a yield stress. So we're comparing the local membrane stress to the yield, which in general for piping has always been considered a primary type analysis, not a thermal analysis. PL plus PB plus Q has always been less than 3 SM, which is 2 SY, which is a shakedown or a ratcheting analysis, which definitely has thermal, as the new 2007 says it does. The fatigue analysis, of course, has thermal, so these have always had thermal before. This one, in general, it hasn't. But it's clear the new 5.6 section of 2007 Division 2 says that the PL classification will definitely include the thermal effect due to the restrained free end of our attached pipe. The way we've always looked at this before is PL less than 1.5 SM has limited the stresses due to principally weight and pressure stresses. Then PL plus PB plus Q, due to the thermal expansion between anchors, has been less than 3 SM so that we don't ratchet the pipe. And PL plus PB plus Q, should be plus F in here, is less than SA, which is the fatigue allowable, so that we don't cause fatigue cracks in any of these components. This is the way we've more or less looked at it, or oftentimes we've more or less looked at it before. Now what we're saying is that, well, we may have a lot of thermal expansion energy which acts on that nozzle in a primary capacity. And so to be conservative, we're going to include that thermal expansion in the primary evaluation of that nozzle. So this condition can produce a primary analysis or a primary condition on the nozzle, or long axial runs with short offsets and elastic follow-up can also produce a similar condition where the elastic analysis doesn't give us the right evaluation or an accurate enough evaluation of the plastic strains in the nozzle. And in those cases, a PL classification for thermal strains or thermal stresses is considered a little more appropriate. So two somewhat special conditions have now govern the 5.6 requirements for 2007 Division 2. So what it says is that for our nozzle neck, M over Z plus PD over 4T, which was our piping evaluation, must be less than 1 times SH. New Division 2 requirement. Additionally, the new Division 2 tells us that the local membrane stresses caused by the moments and pressure must be less than 1.5 S, and the moment should include thermal expansion due to piping, attached piping. And then the membrane plus bending stresses due to moments, pressure, and temperature must be less than 3 SM. This is the typical one. This is the one of concern. This is a little bit new. So now what we'd like to do is see how these play out in real nozzle configurations. I'd like to re-summarize the casting that we've just done in going from piping to pressure vessels. Previously we said that this was the piping allowable, and we realized that this piping allowable, this primary allowable for piping, can be fairly small because SH can be a fairly small number. And all of our secondary allowables before, or our secondary stresses before, are moments due to thermal. This was moments only due to pressure and weight. This is moments due to thermal. This was always, the allowables for the thermal moments was always fairly high for the piping analysis, because even though SH was included, SC was also included, which doesn't get smaller with temperature. So now what's happened is we're putting the moments due to temperature up into this equation and comparing it to a fairly small allowable. So the question is this really what Division 2 wants? And the answer that I think we'll see is that no, this is not what we're doing. What it says is that the PL classification, which PL is the local membrane stress. So item 1 here is the M over Z, which is the beam bending stress. No stress intensification factor has got to be less than SH. The PL, which is the local membrane stress, has got to be less than 1.5 SH. And this includes thermal now, and which it didn't for a lot of analyses before. So what we want to do is we want to come and see what effect this has. The third requirement always had thermal in it. So there's no questions about including thermal in this bending moment. The question again is including thermal in the local membrane stress calculation, comparing to the yield allowable. The way we want to compare those numbers is I want to calculate the allowed nominal stress given the different code approaches. So B31.3 is a piping code approach. So the piping code says that I times M over Z, which is the nominal stress, is less than my allowable. So to calculate the nominal stress allowed only, I'll divide my allowable stress by I to get the maximum allowed nominal stress. I'm going to use 2 I factors. One is the typical Appendix D I factor for B31.3. The other is the reduced branch I factor, which you see in B31.1 and which is available as an option in many pipe stress programs, Caesar for example. So we're going to see 2 B31.3 calculations for maximum allowed nominal. One is going to be due to the essential or the basic B31.3 Appendix D calculation, and the second is going to be including the branch stress intensification factor calculation from B31.1 and Class 2 and Class 3 nuclear codes. WRC107 gives us, through correlation equations of finite element runs, the ratio of the local membrane stress divided by M over Z, or the nominal stress in the branch. It gives us that as a function of D over D, D over T, and T over T from FEA correlations. My PL, my local membrane stress, is going to be less than 1.5 SM. So PL is going to be the function times the nominal allowed nozzle stress, and that's going to be equal to 1.5 SM to get my allowable. So M over Z can be taken as 1.5 SM divided by the function given to me in 497, which is the ratio of PL over MZ. So that will give me the maximum allowed nominal stress that satisfies this requirement. And I want to compare this one to this one for nominal stresses. Additionally, WRC497 gives me the same correlation for PL plus PB plus Q stress intensities. So I can do the same. I can divide the function given to me in WRC 497 by m over z to get the PL plus PB plus Q. I can set it equal to 3SM. I then pull this to the other side to get the nominal maximum allowed nozzle stress. And I'm going to plot four values. M over Z, maximum allowed nominal nozzle stress to satisfy the PL less than 1.5 SM requirement. I'm going to plot the nominal stress to satisfy the PL plus PB plus Q less than 3 SM requirement. And I'm going to plot the nominal stress as required by the B31 code to satisfy both I factor requirements. So let's take a look at what those plots tell us. What you see from this plot is for a wide range of D over T's, for a wide range of T over T's, where T is the thickness of the branch pipe, little t, big T is the thickness of the run pipe or vessel, big D is the diameter of the vessel, big T here, of course, is the thickness of the vessel. So what we've done is we've plotted the nominal allowed nozzle stress, M over Z, for each of those four methods. Here's D over D of 0.3, D over D of 0.5, D over D of 0.75, D over D of 0.9, D over D of 1. It is interesting to watch how the four track with each other. So what we want to know is how does the requirement for 1.5 SM compare to the requirement for 3 SM? So if we come down and look at the D over D ratio of 0.3, i.e. expand the plot, what we see is that the gray line and the green line track fairly closely. And the gray line is the B31B reduced branch stress intensification factor nominal, and the green line is the 3 SM requirement. The 1.5 SM requirement that we are asking about always is a high, almost always, is a modestly high nominal stress. So as long as we check our other requirements, the 3 SM limit will govern before the 1.5 SM limit on membrane stress will govern for thermal stresses for this particular set of criteria for out-of-plane loads. So for out-of-plane loads only, including 1.5 SM in the set of requirements doesn't do very much for us. Doesn't cause too much of an effect. Even though it looks bad, it's not really so bad. Here's the same plot for D over D of 1. It's interesting now, of course, to look at the relationship between these four. So for this particular D over T ratio, for a D over D of 1, these are T over T ratios. This is what the B31 code would allow for a nominal stress in the pipe, essentially around 7,500 psi. The 3 SM requirement would only allow 2,000 psi. So our piping allowables are quite a bit higher in certain cases than our Section 8 requirements. We've done an awful lot of piping for the last 50 years to these requirements. So we have to wonder, and we'll see when we start comparing to some test data, if these are good, but just a little bit on the conservative side in terms of requirements. The next question we want to try to ask is, the previous plots were all based on an SC and an SH equal to 20 KSI. Does the 1.5 SM control now when the hot allowable drops? Because if you recall, that's when we said that it was had the most impact on the criteria. So here is a reproduction of the plot with a reduced hot allowable. We go to a closer look for D over D of 0.3 like we did before. We can see that indeed the 1.5 SM requirements indeed did drop down, but they still don't quite govern. They govern in some cases. In fact, they govern in some cases where piping's involved. But the 3 SM requirement is in almost all cases still controlling. So including 1.5 SM for out-of-plane nozzle loads in our thermal analysis will really likely have little effect on our conclusions. So this, we just stated the conclusions here. The only caveat is that the effect of pressure interacting with those external moments may artificially produce low allowable external loads when we include pressure with that local membrane stress. And unfortunately, the interaction of pressure and the moment was not evaluated in WRC107. So the only option we have now, as soon as we include the pressure stress and find that the new requirement kicks us over the allowable, when everything else says we're okay, is we can certainly compare to the piping codes and see what the piping codes would have done and have done for the last 50 years. Or we can determine if an additional analysis, FEA, is warranted to evaluate the interaction of pressure and membrane. Unfortunately, oftentimes what will happen when we run the elastic FEA and include free end thermal displacements on systems with the membrane stress less than 1.5 SM, we'll see that stresses are excessive, and we'll have to run an ElasticPlastic calculation with consideration of large rotation and show that they're not excessive. We'll come back to this. Now what I'd like to do is get a feel for where the external loads are with respect to actual piping systems. Here's a typical fatigue test. Here's the strain range that was cycled through for this fatigue test. The strain range that we saw here was 2.7%, no visible distortion, 240 cycles to failure. So there was no collapse, no distortion at 2.7% strain in a 4-inch size-on-size component. Let's go to a WRC 230 model, C2, D2, deformations for out-of-plane bending moment. Here are the strains versus the load. Here is the maximum load applied to the T. Here's 0.2%, so this would be the 0.2% offset for this particular strain gauge. What we see during the test is that these strain gauges are the strain gauges located at this point on that intersection, this intersection. These strain gauges were in a more highly stressed area because they're straining quicker. One of those strain gauges went through strain reversal. As it saw plastic deformation, the other parts of the material that were still elastic began to pick up the load. And we see strain reversal in a few places here. And again, 70,000 inch-pounds was the maximum applied external moment to that nozzle. I'd like to go back through the calculations now for our M over Z at 1.5 SM, our M over Z at 3 SM, our B31.3 Appendix D calculation, and our B31.1 reduced branch stress intensification factor. So I'd like to calculate the allowed nominal loads for this intersection, and I'd like to put them on the plot. So B31.3 Appendix D, the external load calculation that we've been running for piping for the last 50 years, would give us this allowable load. The 1.5 SM requirement would give us this allowable load. And the 3 SM and the B31.1 reduced branch equation would give us these allowable loads. So here is, looking at this plot, you can get a feel for what the safety is for allowed external loads in a primary condition on an intersection. Let's take a look at this intersection in an FEA calculation and put the 70,000 inch-pounds on the intersection. Now, shell models are used quite often for this evaluation in EPRI, in WRC 429 or WRC what was it, 479, I believe. The WRC 429 gives the intersection model that's recommended for shell calculations. This is done automatically in Nozzle Pro or FE107 or FE pipe. The ANSYS models, though, can be built easily as well, but again, please follow the WRC 429 intersection recommendations. So either way, we build the finite element models. One of the nice things about FE107 is it does compare the FEA result to 107. So for this intersection, we can see that FE107 would be giving us very conservative axial results, 4 to 5.6 reasonable in-plane results, 9.5 to 14 reasonable out-of-plane results, and certainly reasonable torsion results. If we plot the 70 or generate the finite element results for the elastic model with the collapse load of 70,000 inch-pounds, and then plot the areas of the model that are in excess of 2SY, this is what we see. So here are the parts of the model that are in excess of 2 times yield for the collapse load on this fairly thin intersection. If we go back to the plots of strains, take our calculated maximum stress, which is 267,000 psi for the collapse moment, divide by the modulus, we get a strain of 0.009 or 0.9%, which is right about here, which is a very reasonable calculation for the elastic finite element model. What that says is that our real allowables, which are significantly smaller than this, really give us a pretty good safety for collapse on due to external loads. I'd like to compare just quickly the correlation equations from WRC107, from a Weiss-Rodebaugh correlation, again with shell models, and for this particular D over T and a variety of D over Ds, Nozzle Pro FE107 solutions. So here are the FEA solutions for this intersection with this variety of D over Ds. Here is the WRC107 result from correlation equations from shell finite element models. Here's the Weiss-Rodebaugh correlation equation from shell finite element models. So we notice several things. One, which is the peak at the D over D ratio of about 0.75. So there is the stress intensification factor error at D over D of 0.75 for out-of-plane bending moments. We see that the correlation equations from 497 to the Weiss-Rodebaugh calculation are about 12,000 to about 21,000. So even though the shapes are the same, the accuracy of our anticipated correlation equations is about this. The actual shell calculations do tend to fall somewhere in between. The reason I put this slide up is so that we don't expect great accuracy from correlation equations, and that we don't, certainly, even though a correlation equation doesn't show up in the code or in an excellent WRC document, we don't believe that we're going to get either accurate finite element results to match it perfectly or test results to match it perfectly, unless we're lucky. Now I would like to shift and talk about elastic-plastic analysis methods. There are typically 2 types of inelastic options available in the 2007 Division 2. One is the lower bound limit analysis, which is relatively easy to run. The other is the elastic-plastic analysis. The lower bound limit analysis is stated to be only for primary loads, although you'll have to go back and ask yourself if the extensive thermally expanding piping system provides a primary load. The elastic-plastic analysis can be used for any loading state. It can be used to optimize designs. You can find significant reductions in the minimum wall thickness can be achieved, i.e. you can set your wall thickness based on your elastic-plastic analysis, and you can easily save 25% or more on material costs. This is anticipated to be routine. So we're thinking that certainly in the next few years we'll probably be seeing more elastic-plastic analysis. Or we'll certainly be learning that we don't need a lot more elastic-plastic analysis because we've run a considerable number of them. Even if material savings are not important to you, you'll find that the elastic-plastic analysis will permit greater loadings. And this is oftentimes common when customers revise loadings after fabrication or construction is already underway. Let's talk about the lower bound limit analysis. This is intended to represent an idealized lower bound estimate of the actual load to cause plastic collapse. This ensures that unrestrained plastic deformation doesn't occur. Simple example of this is with a bar. An axial limit analysis of a bar is when the F over A stresses, or the axial stress on a bar, is equal to the yield stress. The yield stress for use in the elastic perfectly plastic material model is approximated by using 1.5S. This is the yield strength. The ASME load requirement is to use 1.5 times the expected load. So essentially we're doing a lower bound limit analysis on the hot allowable stress. Unfortunately, the lower bound limit analysis is not recommended for out-of-plane loadings on nozzles or intersections, or combinations of pressure with out-of-plane loadings on nozzles or intersections. So when we're interested in the combinations of out-of-plane loadings on nozzles and intersections with pressure, we can only go back to the elastic plastic analysis. It is stated that thermal loads are not valid and should not be analyzed, as they are strain limited and the lower bound limit approach is invalid. Although again, we have to go back to the large deflection, excessive elastic energy piping model and decide if this is truly the case for that. But again, the answer is always elastic plastic finite element analysis. So now let's go and let's talk about elastic plastic analysis just for a minute. Elastic plastic analysis attempts to predict the actual collapse load or strains in your structure by taking account the true stress strain behavior, although not the actual material, the true stress strain behavior from stress strain curves developed in the new 2007 Division 2, and the geometric effect. So if you have a guitar string effect where you're pulling on a guitar string and clearly it gets stronger as you stretch it, the large rotation capability or the large rotation requirements will provide that additional strength in the elastic plastic requirements of the 2007 Division 2. Primary and secondary loads can be evaluated. Large displacement theory must be considered. It also includes the effects of strain hardening, which the limit analysis does not include. And this is the lowest safety factor is provided for the elastic plastic analysis that we get in the Division 2 code, which is 2.4 against collapse. So why use an elastic plastic analysis? Well, it's very simple. It provides a go or no-go answer. The structure either collapses as per the loads given in tables 5 in part 5 of 2007 Division 2. It either collapses or it doesn't. The strains either satisfy the fatigue and the ratchet spring requirements or they don't. This may be particularly beneficial with very complex three-dimensional shapes where it is difficult to stress linearize those results. This can save money. These more accurate analyses also allow us to reduce the required thicknesses, and we don't have to guess about whether thermal analyses or thermal loads should be included in local membrane stress categorization or not. So elastic plastic analysis with the consideration for large rotation solves a lot of the problems we've been talking about. So conclusions. Relatively straightforward shell FEA can answer a considerable number of questions about combinations of loads. When you do this, please remember that boundary conditions of freeing one end of the vessel or the header provides the most conservative stress assumptions. Small d over d, for small d over d's, appendix D of B31 may be non-conservative, although including the branch reduction stress intensification factor, as we saw or see in B31.1 and in section 2, and for example, as Caesar permits, may bring the allowables more in line with ASME section 8 requirements. Very high local elastic FEA type stresses may be very far from failure when you're considering collapse. We saw that with the example problem earlier. Although these very high local elastic FEA type stresses are still objectionable from a fatigue crack point of view. So it is fatigue that controls these high local elastic FEA type stresses. Whether membrane limits are included or not, we saw does not make too much difference when out-of-plane loads only are investigated. When you include pressure, although, you'll probably find there's a little bit more of a problem, although we've never had that problem before, certainly not with piping. EN13445 does not include the thermal component for membrane evaluations for membrane stresses. So piping codes, European codes, do not provide for the thermal requirement in the local membrane stress evaluation at nozzles. More than likely, any problems in your piping system and your nozzle connected to your vessel are going to be due to incorrect stiffnesses and incorrect evaluations of the loads, far in order of the errors due to the categorization, or because your friction modeling is incorrect, or because you've provided unstable friction systems, i.e. the pipe walks around because there is no axial or no axial stops or guides where you have very small thermal displacements, as we saw in the example from last week. So we think item number 6 is where you should pay attention mostly. Unfortunately, if you try to follow the 2007 Division 2 rules to the letter, you may find that you end up doing a more elastic plastic analysis than perhaps is required. In fact, we think than is going to be required. And unfortunately, WRC107 won't address this pressure membrane issue too effectively because it doesn't include pressure stresses in the evaluation. The remaining PRG webinars for this month and next month, next week is buckling of piping components and pressure vessel components. We'll take a look at the new codes, the new Section 8 Division 2 2007 rules for buckling and how they affect nozzles. On April 29th, there'll be an excellent discussion on FRP or GRP pipe failures and lessons to be learned. That discussion will be given by Dr. Hans Boss. On Thursday of that same week, we'll have the piping and pressure vessel ethics webinar. And then in May, we've been asked to provide more real examples of piping systems and how you would make the calculations. So May is our piping and problems to avoid month. So what we'll be doing is demonstrating a number of examples, showing the actual calculations, and showing what's to be done. And then at the end of May, we'll have the CAD and pipe stress webinar, where we will discuss what happens when you move from a CAD model into a pipe stress model and the typical errors that we see when that's done. Again, please email any questions to web044@pollen.com, and we'll try to get to them within 24 hours, hopefully within 24 hours, providing there's not too much of a backlog with things. And then please also email web044@pollen.com and ask for a copy of this presentation if you would like one, and a 1-hour PDH certificate. Your email address must match the webinar registration email so that we can make sure that the PDH certificates are reasonably validated. Again, thank you very much for your attendance.
The top of the slide has 2.
So how did that one go? A little confusing.